Okay, we continue with 10.2 in Barnett, and now we look at limits at infinity. So not only is infinity a symbol used to describe the behavior of limits that do not exist, as we saw in the previous video, but the symbol infinity can also be used to indicate that an independent variable is increasing or decreasing without bound. It's getting really, really large without bound. We'll often write x approaches infinity to indicate that x is increasing through positive values without bounds. It's just getting bigger and bigger. And x approaches negative infinity to indicate that x is decreasing without bound. So it's getting more and more negative. That's how you should think about it. It's getting smaller and smaller, which means it's getting more and more negative through the negative values. Okay, so then we could talk about limits at infinity of power functions. Well, we begin our considerations by first looking at what power functions are. And we're going to look at power functions of the form x to the power of p and 1 over x to the power of p, where p is going to be a positive real number. Okay? Now, if p is a positive real number, then x to the power of p increases as x increases. Right? Think about your basic x squared or x cubed or even x to the 5.7 power. As x gets bigger and bigger, this output is going to get bigger and bigger as well. Well, it could be shown that there is no upper bound, in fact, on the values of x of p. You could just keep growing without bounds. So we indicate this by writing the following sentence mathematically. X to the power of p approaches infinity as x approaches infinity. In terms of limits, we say the limit as x approaches infinity of x to the power of p equals infinity. Right? Once again, this limit does not exist. Okay? Just because we set it equal to infinity does not mean anything. Infinity is not a number. We're just saying equals infinity because this gives us a better idea of the behavior of this function x to the p as the inputs get larger and larger. Okay, the limit itself does not. Okay, why don't we take a look at more of this? So, since the reciprocals of very large numbers are very small numbers, it follows that 1 over xp, the reciprocal of x to the power of p, approaches 0. As x increases without bounds. Right? If x to the power of p gets really, really big, well, as x increases without bound, then 1 over x to the power of p must get really, really small and approach 0 as x increases without bound. Once again, how do we write this mathematically? We say 1 over x to the power of p approaches 0 as x approaches infinity. Or in terms of limits, the limit as x approaches infinity of 1 over x to the power of p is 0. The best way to see this is to graph such power functions. So in here we did it for the classic x squared, and for its reciprocal 1 over x squared. Okay, so here's those two functions graphed. G of x equals 1 over x squared, and f of x equals x squared. And notice, as x increases without bound, excuse me, as the input here gets bigger, the limit as x approaches infinity of the quadratic function x squared is infinity because this function shoots up to positive infinity. On the other hand, if you look at the limit as x approaches infinity of g of x, as x gets infinitely large, this function gets closer and closer to 0. So this limit is 0. Okay, so in general, if p is a positive real number and k is a non-zero real number, then the limit as x approaches infinity of k over x to the p is equal to the limit as x approaches negative infinity of k over x to the power of p, and it's equal to 0. That's always going to be the case. Also, the limit as x approaches infinity of k times x to the p is either positive or negative infinity, depending on the value of k, and the value of p as well. Likewise, the limit as x approaches negative infinity of k times x to the p could be positive or negative infinity if it is defined. Notice, k and p determine whether the limit at infinity is positive infinity or negative infinity, right? This constant term, for example, could be negative, and it would turn the whole thing around. The last two limits are only defined if the pth power of a negative number is defined. This means that p has to be an integer or a rational number with odd denominator. That's another thing you have to be aware of when you work with these. Okay? Well, let's talk about limits at infinity of polynomial functions. Well, as x increases without bound in either the positive or the negative direction, the behavior of the polynomial graph will be determined by the behavior of the leading term, the highest degree term, right? That's what we call the leading term. the leading term will either become very large in the positive sense or in the negative sense, assuming that the polynomial has degree at least 1. In the first case, where the leading term will become very large, in the positive sense or in the negative sense, the function will approach infinity, and in the second case, the function will approach negative infinity. In mathematical shorthand, we write this as the limit as x approaches positive or negative infinity of f of x equals positive or negative infinity. This will cover all possibilities. Okay, so the polynomials are not bad. Alright, so why don't we talk next about horizontal asymptotes? We've already discussed those in our class. Well, a line y equals to b is a horizontal asymptote for the graph of y equals f of x if f of x approaches that value b as either x increases without bound or decreases without bound. Symbolically, we say y equals to b is a horizontal asymptote if this limit takes place, or if the limit as x approaches infinity of f of x is b. In the first case, the graph of f will be close to the horizontal line y equals to b for large negative x in absolute value, right? Because we approach negative infinity. In the second case, the graph will be close to the horizontal line for a large positive x, right? Because we approach positive infinity. What we want to remember is that it's enough if one of these conditions is satisfied. But frequently they both are. I mean, it just so happens that most of the cases, both of them will be satisfied, but you only need one to be true. So as an example, here's the figure that shows the graph of a function with two horizontal asymptotes. So we have y equals to 1 and y equals to negative 1. And why are there two? Well, because as x approaches positive infinity, this graph will approach the line y equals to 1. And as x approaches negative infinity, this graph will approach the line y equals to negative 1. So we have two horizontal asymptotes in this case. Why don't we take a look at the next slide here, horizontal asymptotes of rational functions. Remember, rational functions are just two polynomials, right? Two polynomial functions, one on top of the other. Well, using our knowledge of polynomials, we say that the limit as x approaches positive or negative infinity of f of x is simply the limit of the leading terms of the polynomials. Okay, that's what we have to worry about. And you guys remember those three cases that we had from chapter 3 with horizontal asymptotes. So here they are again. If the degree of the top is less than the degree of the bottom, then the horizontal asymptote is 0 and the limit is 0. If the two degrees are equal, then the limit is simply the ratio of the two, I should say, leading coefficients, am over b sub n. And the line is the horizontal asymptote. Finally, if the degree of the bottom, of the top, is bigger than the degree of the bottom, then this function does not have a horizontal asymptote. Review those three cases. We've already covered them in our class. Okay, so notice that in cases 1 and 2, on the previous slide, the limit is the same if x approaches positive or negative infinity. It wouldn't make a difference in both cases. Thus, we say a rational function can have at most one horizontal asymptote. That's the reasoning behind it. Notice that the numerator and denominator have the same degree in this example, 2, right? So the horizontal asymptote is the ratio of the leading coefficients of the numerator and denominator, which is 1.5. Also notice that the horizontal asymptote actually crosses the function at this point. That's okay. That might happen. So keep that in mind. That's perfectly fine. And why don't we look at these examples? How to find the horizontal asymptote of each function. Okay, well, all you have to do is apply the rules that we just learned about the degrees. In the first one, the leading coefficient is 3, but the degree of the leading term is 4. And on the bottom, the leading term has degree 6. So since the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is simply y equals to 0, the x-axis. In the second example, the degree of the numerator is greater than the degree of the denominator, so there is no horizontal asymptote. Okay, and that's our solution essentially. So to summarize, an infinite limit is a limit of the form that you see here, y goes to infinity. It is the same as a vertical asymptote, okay, as long as a is a finite number. A limit at infinity is the limit of this form, x goes to infinity, and that's the same as a horizontal asymptote, as long as L is a finite number.